Welcoming Joel Tropp, who's the Steele Family Professor of Applied and Computational Mathematics at Caltech. He's well known for work in sparse approximation, randomized numerical linear algebra, and matrix concentration. And he has the rare distinction of making results that are new look old. Because he's able to write papers that are so clear, so well motivated, with bounds that are so user-friendly that you cannot believe that they were not known before. But in fact, the reason they were not known before is that it's hard to write that well. It's hard to see that clearly. That you can make one of these results look easy and simple. And as a result, he's actually known to obfuscate, to hide new results under the guise of old results. And for example, his very well-regarded paper in SIAM Review on randomized numerical linear algebra. And so SIAM Review publishes reviews, so the results should not be new. Okay? But in fact, many of those results are new. So this is a flagrant violation of their rules, and yet
that's not a rule of the
Okay. Anyway, we're very happy to welcome Joel Tropp.
Thank you for the generous introduction, Neville. Before I begin, I would like to call your attention to the existence of a new journal, which will be published by SIAM, called the SIAM Journal on the Mathematics of Data Science. We are accepting submissions. The first issue will appear imminently. And we cover all aspects of data science with a focus on foundations. So this includes signal processing, statistics, information theory, control, optimization, theoretical computer science, applied math, applied probability, anything that is motivated by problems of interest in understanding data. We hope that you'll consider us if you write papers in this area and send us your best work. This is a generalist journal. We're really hoping to form the nucleus of a community of researchers in data science, and so our aim is to publish papers of wide interest. And we hope that, as I said, you will submit and that you will read papers that appear starting very soon. Okay. Now, to the main event. My talk today is titled Applied Random Matrix Theory. So this is in a long tradition of taking an established area of mathematics and attaching the word applied or computational to the front and declaring that there is a new field. So some examples include applied algebra, computational topology, and the most successful all, applied mathematics. So this is a lot like random matrix theory, but it is motivated strongly by applied problems, many in data analysis. And that's perhaps the distinction between the, not called theoretical random matrix theory. Okay, good. So I guess before we get started, we should make sure we all agree about what we're talking about. So what is a random matrix? So a random matrix is a matrix, which is to say a rectangular array of numbers. And what makes it random is that the entries in that matrix are random variables that need not be independent from each other, so they can be correlated in complicated ways. So I have here in activity a random matrix. And so I'd like to call your attention to a few features of this example. First of all, some of the entries are not random. So you can see that there's zeros on the diagonal and the counter diagonal. And so it's got structure. It's got a sparsity pattern. Moreover, even though this number is random and indeed is drawn from a standard normal distribution, you can see that it's repeated along the super diagonal here. And similarly for the entries on this super diagonal and this super diagonal. So you can see that these numbers, even though they're random, are not independent. And so this is a feature that's typical in a lot of contemporary applications. You have random matrices that have complicated structure and a lot of internal dependencies. So random matrices, lots and lots of things. And the question is, what is it about random matrix theory that makes it different from probability? And the answer is that as compared with a random number or a random vector, a random matrix is a linear map. It acts on vectors to produce other vectors. And we're interested in understanding its behavior as a random linear map. So if the random matrix is square, we might be interested in its eigenvalues or its eigenvectors. Again, these are both connected to its action as a random linear map. If it's a general random matrix, potentially rectangular, we might be interested in its singular values or singular vectors, again, connected to its action as a random operator. And more generally, if you think about this acting between two norm spaces, you might be interested in understanding its operator norm. So again, what makes this field distinctive as compared with other parts of probability is the focus on the properties of the random matrix as the linear map. Okay. So let me tell you a little bit about the history of this field. This talk is written under the principle that everyone should understand at least half of it. Things will get a little bit crazier in the last few slides. I'm going to accelerate to close to light speed. But for now, let's go back to the early days of this subject. So Peter Forrester told me that the actual origin of random matrices is in work on invariant theory, so averaging over groups. And so, for example, if you take a function over the orthogonal group and you evaluate its average over the entire group, this is the expectation of a function of an orthogonal matrix, or drawn uniformly at random. So you can indeed see this in some early papers of Hurwitz from the late 19th century, but I think it's maybe a little more visible when you start looking at the statistics literature in the 1920s. So this gentleman here is Tom Wishart. He was a student of R.A. Fisher, and statisticians already were interested in understanding multivariate data, even back in the 1920s. And, so one thing you might ask about multivariate data is what the correlations or the covariances are among the variables that you've measured. And one way you might accomplish that is by going and querying a bunch of individual subjects about the values of their variables. So go to the freshman and ask them what their GPA is and what their SAT scores are, and how many hours of sleep they get every night, and so forth. And after querying a bunch of individuals, you hope that you get independent answers from them, and you'd like to use this data to estimate how these variables are related to each other. So you can do that by forming a sample covariance matrix. So you take each subject, write down the variables, multiply by the same vector and transpose, and this gives you some very weak estimate for the variance based on that single individual, and then you average over all of the individuals that you've talked to. This is what's called a sample covariance matrix. Now, Wishart was interested in understanding the behavior of a sample covariance matrix for a standard normal, for a normal population. So all of the variables now are viewed as being Gaussian random variables with some correlation structure. And if you make this assumption about your data, the sample covariance matrix has a distribution, which is now called a Wishart distribution. And Wishart worked out the distribution of the eigenvalues of that sample covariance matrix in this rather complicated formula involving determinants and gamma functions and things like that. And so, as I said, even back then, statisticians were interested in understanding the properties of multivariate data, and random matrices come up when you tabulate that data. And this is indeed still the case, that statisticians are interested in the behavior of multivariate data, and random matrices don't play a big role in statistics. And we'll come back to this example later. Surprisingly, the second place I'm aware of that random matrices arose was in numerical analysis. The reason this is surprising is that random matrices were immediately evicted from this field and didn't reappear until about 15 years ago. But here's the idea. So this gentleman here is John von Neumann, standing in front of his computer at the Institute for Advanced Study. So even before John von Neumann had a computer, he was curious about what you might do with a computer once you had one. And one of the things that came to his mind was solving systems of linear equations. And so before he ever had a computer, John von Neumann invented the LU decomposition, which is essentially Gaussian elimination in factorized form, and performed a floating point error, or not floating point, but a rounding error analysis for this algorithm. So in other words, when you take a matrix and you make computations, you make mistakes every time you do a piece of arithmetic because you can't store a real number. And so the approximation of the matrix, A equals L times U, has some errors in every entry. And in a, so von Neumann did this in a 1947 paper with Goldstein in the Bulletin of the MS. And there's a second version, part of this paper that appeared a few years later, where they said, well, imagine that these floating point errors, these rounding errors, I don't think that they're going to be worst case, like we're always going to make a horrible mistake, or the same horrible mistake in every entry. What if we try and find a better model so we can understand how badly we've done making this computation? So let's assume that the errors are random. And so von Neumann said, okay, let's model the errors and making the rounding errors in this computation as Gaussian variables. And let's try and understand the norm of this matrix of Gaussian variables as a way of trying to assess the typical error you make in this computation when you perform it in finite precision. Okay. And so here is an excerpt from this 1951 paper where he computes the probability that the norm of this random matrix exceeds some level and gives a sort of complicated bound here. So one thing I'd like to point out is that, again, the random matrices he was considering are very, very structured. All the entries are Gaussian, they're all independent, and they all have the same distribution. And so it's a very nice random matrix as these things go. And what again, is surprising is that this random model appeared very, very early in the history of numerical analysis. For a lot of reasons, numerical analysts actually kind of hate randomness, and so random matrices more or less disappeared from this field for quite some time. Okay, good. The third, perhaps most famous place that random matrices arise is in nuclear physics. So this gentleman here is Eugene Wigner from the photo that was taken after he was awarded the Nobel Prize. So in the late 1940s, Wigner had the surmise that Wigner was interested in studying slow nuclear reactions involving heavy atoms for reasons you might be able to define. And the problem with these computations from the point of view of physicists is that they're very complicated. These atoms have a lot of protons and neutrons, and as a consequence, it's not so easy to actually make any of these computations explicitly. And so Wigner had the surmise that instead of studying the Hamiltonian of this reaction itself, instead he might study a random Hamiltonian that had the same symmetries as the Hamiltonian of the reaction that he cared about. And he hoped that by understanding the eigenvalues of that random matrix, that random Hamiltonian, that he might get some insight into the energy levels of the true process. And so he wrote a paper in the late 1940s that made this sort of supposition. And then in a very famous paper in the Annals of Mathematics in 1955, he gave some mathematical substance to the model he was interested in. So he framed what is now called a Wigner matrix. I'll show you one in just a moment. And he calculated the density of the eigenvalues of Wigner matrix as its dimension goes to infinity. So he found what's called the limiting spectral distribution of what we now call the Wigner matrix in this paper. And the hope was that by understanding the eigenvalues of this matrix, you could indeed understand the energy levels of an atomic reaction. As it happens, that's not true. But it does turn out that the spacing between the eigenvalues of this matrix is descriptive of some kinds of physical processes. And this paper is somehow the paper that launched 1,000 ships and was really the source of the modern field of random matrix theory. There are other random matrix models that came out of the physics literature, was the Dyson threefold way, as it's called. These very highly structured random matrices also found their way into other parts of mathematics, including, for example, number theory in the 1970s when Hugh Montgomery proposed that the eigenvalues of a random orthogonal matrix are a good model for the behavior of the zeros of the Riemann zeta function. And so there's a massive literature now in mathematics on random matrices that really was instigated by Wigner's work. Okay, now let's get a little more concrete. All of what I'm describing to you is what I would call classical random matrix theory. This concerns matrices that are very symmetrical in the sense of group theory. So let me try and explain what I mean by that. So here is an instance of a Wigner matrix with dimension 7. So there's zeros down the diagonal. In the superdiagonal, each entry is independently chosen and is equally likely to be +1 or -1. The entries in the lower triangle are copies of the entries in the upper triangle. It's a symmetric matrix. And so the symmetry here comes from the fact that all of the entries are independent, and so the distribution of this matrix is is identical under symmetric permutations. So no matter how you reorient the rows and columns, you'll get another Wigner matrix. And there's also a lot of statistical independence here, which means that on some level the matrix has really got a lot of it's very nice. That's the technical term. All right. So here is a picture of what Wigner proved in that Annals of Math paper. So here is for a Wigner matrix of dimension 1,000, the histogram of the eigenvalues of one draw of a Wigner matrix. This is not an average. So I made one Wigner matrix, I computed its eigenvalues, and I made a histogram. And overlaid on top, you see this blue curve here, which is what's known as the Wigner Semi-Circle Law, which is the limiting spectral distribution of a Wigner matrix. And you can see that even for one realization of the matrix, this limiting law is already a beautiful description of the histogram. Okay? And so what you learn from this picture is that the results are indeed very precise. They're already descriptive even for relatively small problems, and that's true even without averaging. So classical random matrix theory concerns these very symmetrical models and gives very detailed results. And by now, we understand basically everything there is to know about the eigenvalues of a Wigner matrix, including microscopic fluctuations on, scales of 1 over n, and it's really a very complete detailed theory. And because of these symmetries, there are very strong resonances with other fields of mathematics as an eigenvalue joke. Not very good. Anyway, and this is why, for example, these ideas also appear in areas like number theory. Okay? It's these symmetry properties that mean that these the tentacles of random matrix theory reach out into other fields. Okay. Now, great. We know everything about Wigner matrices. Are we done with random matrix theory? Do we need to continue? So I'm actually going to Ann Arbor tomorrow for the AMS sectional meeting for a workshop called Beyond Wigner and Wishart. These two gentlemen on the previous slide. So the answer, of course, is no. And let me try and indicate why it is that the theory is not finished, even though we know everything about random matrices. So random matrices have actually found their way into a huge number of contemporary fields, including all of these examples, and I have drawn one paper from each of these areas at random, not uniformly, and every one of these papers has random matrices, and they concern this range of subjects. And so you can imagine when you see this dizzying variety of areas and problems, you might imagine that the random matrices don't all look like a Wigner matrix. They might look a little more like that random matrix on the first slide, which is decidedly not Wignerian. Okay, so let me give you a more concrete example of the kind of matrix you might care about if you were doing data analysis. So one thing that people like to do when they have a lot of data is throw some of it away at random and hope that somehow the random subsample inherits the properties of the original data that was collected. Okay, so here's a very simple example of that. Here I have in captivity a matrix that someone has handed to me, in this case just the binary representations of the numbers from 0 to 15. And this matrix is not random. It's just something that someone dug out of their attic and brought to me as a gift. And what I've done in passing from the top line to the bottom line is to sample columns at random from this matrix. And so now there are only 8 columns instead of 16, and because the columns randomly chosen, this is indeed a random matrix. But on the other hand, because we started with this deterministic matrix here, this doesn't look anything like a Wigner matrix. And so we might be interested in understanding the spectral properties of this matrix, or how well this matrix captures some intrinsic structure that came from the matrix we started with, whatever that means. And so I think key differences with classical random matrix theory is that these days there are a ton of examples, and a lot of them are data-driven. It's things you get by sampling matrices that someone presents to you. Or they come from applications in computer algorithms where the matrices need to have a lot of structure to ensure some algorithmic property. And in a lot of these instances, we don't necessarily care about achieving the same precision of results that Wigner was able to obtain. We don't care about producing a semi-circular law for the singular values of a matrix like this, or a quarter circle law. We might be happy in just knowing the norm of the matrix, or knowing how well it approximates this matrix in some appropriate sense. And another difference is that the theory here really still has a long way to go. There's really a lot we don't understand about the problems we're studying now. So it's a rich area for further research. Okay, good. So the thesis of this talk is that modern applications demand new random matrix models and new analytical tools for understanding those models. So let me pause and ask if there are any questions on what we talked about so far. When they learned me to teach at the University of Michigan, they told me that after you ask a question, you have to wait 10 seconds to see whether anyone actually has any questions before you're allowed to move on. So now that I've done that, my experience in teaching is actually usually takes about 1.5 minutes. It makes for a very awkward pause. Okay, good. So let me start out by telling you about the kind of results that I'm going to be trying to establish. And these are a lot different in spirit from the density of states results that I showed you before, these models for the limiting spectral distribution eigenvalues. So if someone hands me a random matrix, my goal is to find probabilistic bounds for the difference between Z and its expectation in L2 operator norm, spectral norm, largest singular value, whatever you prefer to call it. Now, to clarify what I mean by the expectation of Z, this means that I take the expectation of each entry of this matrix and put it in the corresponding entry of this matrix. Okay? Expectation is linear. You really just take the average of each entry as Z. Okay? So this is a matrix, this is a matrix. Somehow I hope that Z fluctuates around its mean, and I'm going to measure the size of the deviation using the operator norm. Okay? Now, why is it that this is a good thing to do? Well, as it happens, there are a lot of random matrices that do indeed concentrate around their mean. And why the operator norm? Because I get a lot of things for free from a bound of this form. So in particular, it tells me that the singular values of Z and its mean are close to each other. And so if I know the mean, I can get good estimates for the singular values of the random matrix and hold with probability. If the expectation has isolated singular values, then the singular vectors of the expectation are stable, and I can guarantee that the singular vectors of z are close to the singular vectors of those isolated eigenvalues. Okay. So again, good estimates for singular vectors. This tells us that every linear functional of z is close to the corresponding linear functional of the mean. And this is the most important part, this is what I saved it for last. We get control on the spectral norm of the matrix Z. How do we do that? We use the triangle inequality. Norm of Z is roughly equal to the norm of its mean plus or minus the size of the fluctuations. And so if I can compute the norm of the mean, and I can get a bound on the size of the fluctuations, I get upper and lower estimates for the norm of the matrix. And as it happens, computing the even the expected spectral norm of a random matrix is a giant nightmare most of the time. And so this result actually has a lot of substance all by itself. I should also say that bounds of this form are already useful for studying approximations of random matrices. So if the expectation of Z is some target that I'm trying to approximate, then if I can argue that Z is close to that target, then I've obtained a good approximation. This will come up again later. Okay. Any questions on what we're trying to achieve, what the goal is, and what the outcomes are? Okay. So our goal is matrix concentration, fluctuations of the random matrix around its mean, as measured, and operator norm. Now we need a model. If someone just hands you a random matrix, there's not much you can say about it. It could look like that horrible beast on the first slide, which is not got anything you can really grab onto. So we need a model. Now, so if you've ever taken probability or taught probability, you'll remember that as soon as you finish talking about random variables, you start building models for collections of random variables. And the very first one you see is the independent sum model. And we're going to start there too. So the idea is that we can think about the random matrix Z not as this sort of hermetic object that we have no insight into, but rather we can think about instances where Z is a sum of random matrices, all of which are statistically independent from each other. So I have a whole bunch of summands, I add them up, and get the full random matrix. My hope, of course, is that the summands are simple objects that I can understand more easily. So a useful observation already is that the mean of this random matrix is just the sum of the means by linearity. And so if these SK are simple objects, I can compute the mean, then I just have to do a little bit of linear algebra to get the mean of the whole matrix. That's already valuable. Now, why would we care about a model like this? I mean, am I just making this up so I can do some math? I mean, it's not necessarily a bad result, but as it happens, we've already seen two examples that come from this model. So the sample covariance matrix fits into the independent sum model. So why is that? Each individual that we measure gives us a rank 1 matrix. We believe that each individual, our sample, is independent, and we just add up these rank 1 matrices and average them to obtain the sample covariance matrix. So the sample covariance matrix is indeed a sum of independent rank 1 matrices. Rank 1 matrices, of course, are a lot simpler than general matrices, so you already start to see the value in trying to make this kind of decomposition. Okay. Second of all, this other matrix we saw, where we take a fixed matrix and we subsample columns, this actually also fits into this model if we allow replacement. This takes a little bit more work to see. You can also, if you're willing to accept 0 columns, it's also not hard to see that even without replacement, a matrix where you randomly zero out columns falls into this framework. So this is an exercise for you to persuade yourself that these examples both fit into this sort of general framework, and a lot of other things beside. Okay. Any questions on the model? Yeah.
Every random matrix, in the case of this model, if K ranges over a single set.
Yeah. That's true. And maybe not so useful, but it's definitely true. The hope, of course, is that by breaking it down into little pieces, you're going to somehow isolate the atomic components. And in a lot of instances, this model actually presents itself to you. It's not like you have to go looking for it. So in the case of the sample covariance matrix, it's just staring you right in the face. Okay, good. More questions? Okay, great. So now, how are we going to go about analyzing this model to obtain matrix concentration bounds? Well, you have to think back to your first class in probability, or maybe more likely your first class in randomized algorithms, something. And you will come across the Bernstein inequality, which is a classic result on large deviations from the 1920s. I would like to comment that this result is not due to Chernoff and it is not due to Hofstede. If you're in the Russian literature, when they were still in diapers. Okay, so here's how this result works. We assume that we have a family of real random variables now, S1, S2, S3, and so forth. We're going to assume for simplicity that each one has mean 0. They're all centered. And we're going to assume that each one is uniformly bounded by some number L. L is not a random variable, it's just some upper bound. Okay? And we're going to be interested in understanding the fluctuations of this sum of independent real random variables. And in particular, we'd like to know the probability that this sum exceeds some level t. This is the same kind of concentration result as before because the mean of this random variable is 0. So we're asking how well it concentrates around its mean. But I've suppressed the mean by centering everything. Okay? So I'd like to know the probability that this random variable exceeds some level. You could think, for example, about this as a model for a random walk, if you like. It's where the random walk arrives after some number of steps. Okay? And Bernstein's inequality tells us that there are two phenomena. First of all, the variance of this sum plays a role, which is by independence, just the sum of the expectations of the squares of the summands. So we've used independence and the fact that these summands are mean 0 to see that the variance has this form. And again, it's very easy to compute because we just have to add up the variances of the individual components of the sum. And Bernstein's inequality tells us that the variance plays a role in the following way. When t is not so big, the level that we'd like to understand the sum, if t is not so big, then the probability of a deviation beyond t looks like the tail of a Gaussian with variance b, e to the minus t squared over 2b. On the other hand, when t is larger, then this square cancels this t, and this looks like an exponential random variable with mean at L. So there are two phenomena packed up here, one of which is sub-Gaussian decay with variance v on small scales, and once we get to large scales, we start to see sub-exponential decay on scale L. This result is pretty easy to prove. You add a parameter theta, you multiply on both sides, you exponentiate, you apply Markov's inequality, you beat it to death. This is an elementary result. It's not very hard to prove. Nevertheless, it's extremely useful. Yeah.
Is that an infinite sequence of?
It can be, or it could be finite. It doesn't matter. If it's infinite, that variance better be finite. Yeah. More questions? So Bernstein's inequality is a result for independent sums of real random variables, and it tells us how we can use simple properties of the summands, like their variance and their upper bound, to obtain a global bound on the tails of the sum. All right. So what we're going to do is try and imitate this result in the matrix setting. It's one of the most useful results in scalar probability, so why not try to do this for matrices? This result that I'm going to tell you about has a very long, complicated history that I'm going to suppress completely. But people have been thinking about things like this since at least 1973. So here's the extension to matrices. So we're now going to think about S1, S2, S3, and so forth being independent random matrices, each with the same dimensions, D1 and D2. As before, I'm going to assume that each one is centered, that's mean 0, and I'm going to assume that each one is bounded uniformly by some number L. But it's not a number anymore, so I need some other way of measuring its size. I'm going to use the spectral norm. Okay? So all of these matrices are bounded spectral norm. So this is a sort of local property of each one of the summands. Each one's uniformly bounded. Now, as before, I'm going to be interested in understanding the probability that the sum of these random matrices is far from its mean, which is 0, as measured in the operator norm. So again, this is a concentration inequality. The probability that a random variable, in this case a random matrix, deviates from its mean. And I'd like to know the probability that that random matrix has magnitude bigger than L, where now magnitude is measured in the spectrum norm. Okay, as before, the upper bound is going to play a role, as is the variance. Now, the variance that we're going to use here looks a little different from before. It has two terms, one of which is the sum of the expectations of the squares of the SK, where square means SS star. It has another term, which is the sum of the expectations of the squares of the SK, where now square means S star S. The reason we have both of these terms here is that matrices have both a range and a co-range, and we're interested in the behavior of the matrix on both sides. As a consequence, a matrix has two squares, not one, and both of them have information about the behavior of the matrix. And we actually need both of those things in the matrix setting if we want to understand this sum. Now, what happens if these are numbers? Well, this just collapses to the sum of the expected squares. This just collapses to the sum of expected squares. And so this really just reduces to the variance if these are real random variables. So there's not really much of a difference. Conceptually, this just looks like a variance. But it's been adapted to the matrix setting where we now need to include the left square and the right square. All right, good. Now, as before, the probability that the sum of these independent random matrices is big has two behaviors. One of which is when the level t is small, it looks sub-Gaussian, like a Gaussian random variable with variance v, where now v is this variance and not the one before. When t is larger, again, we see sub-exponential behavior on the scale L. So sub-exponential, like a sub-exponential random variable with mean L. Okay. So this is exactly the same term as before. So medium deviations are driven by sort of averages of fluctuations, like central limit theorem behavior. Large fluctuations are driven by one of the summands popping up and turning out to be unusually large. Okay, now there's one more feature here, which is that we have the sum of the two dimensions sitting in front of the exponential. And this is essential, it turns out, in the matrix setting. But what happens if the SKs are numbers? What are D1 and D2?
1 plus 1.
They're 1. And so this is 2. And this is exactly the constant you see in front of the Bernstein inequality. So, in other words, we have a perfect generalization of the Bernstein inequality, which collapses to the Bernstein inequality in the real setting, but now applies to random matrices instead of to sums of random numbers. Now, one sort of surprising difference between this result and the other one is that this is actually a deep result. This depends on one of the hardest theorems in matrix analysis, which is the joint convexity of quantum relative entropy. And this serves as a replacement for this some of the steps of the simple argument I showed you before. Okay, now this is kind of a confusing result, I acknowledge. So what's the real message here? The message is obtained by integrating this tail bound, and you obtain an estimate for the expected norm of this random matrix drawn from the independent submodel. Remember, again, this is really the fluctuation of this matrix about its mean value, which is 0. So the expectation of the norm is controlled by two things. It's controlled by the square root of the variance parameter times a factor that's logarithmic in the dimensions, so it depends very weakly on the dimension, plus another term that's linearly on the upper bound times another logarithmic factor in the dimension. So the point is that if you want to know the expected norm of a random matrix drawn from this model, so for example, covariance matrix, all you need to do is compute this variance, which is just a matter of doing some linear algebra, and you need to compute this upper bound, which is a matter of doing some linear algebra, and you get for free a bound on the expected norm of this matrix. This is not easy to come by in general. Roughly speaking, all of the terms here are necessary, including the logarithms. So you can't really improve on this result without making extra assumptions. Okay, let me pause and ask if there are any questions on this result. Who cares? Let me start out with a simple example that frankly is not useful, but is gives you a flavor for what you can do here. So imagine that, again, someone hands you a matrix. This is like a data-driven problem. And you feel like this matrix maybe doesn't have a lot of information in it relative to its size. So you notice anything about this example? Yeah, it's rank 1. So there's no reason I need to write down 16 numbers to represent a rank 1 4x4 matrix. I mean, once I know the first row and column, I'm finished. So I believe that there's not a lot of information, so I should be able to compress this matrix. One way you might do that is by sparsification. So you might throw away some entries at random and keep the rest and hope that what you kept is a good approximation of the original matrix. Why does this make sense? Well, how did we do this? We kept the big entries and forgot the small entries under the theory that the big entries are more important. And the nice thing about this matrix is that now it only has half as many non-zero entries, and so you can view this as a compression of the original matrix. People have proposed using this as an ingredient in various kinds of algorithms, but I've never seen a really convincing application of this. But stay tuned. So for a sparse, the goal here of sparsification is to find given a matrix A, to find a sparse matrix A hat that is a good approximation of A in spectral norm. And the approach that I'm going to tell you about is based on non-uniform randomized sampling and exploits the matrix Bernstein inequality in the design and analysis of the algorithm. Okay, so this is really the most technical slide. So how are we going to do randomized sparsification? So suppose that someone hands you a fixed matrix with dimension D1 and D2. What we're going to do is construct a probability mass on the matrix indices. So each entry of the matrix is going to get a probability associated with it. I'll tell you how to do this in a minute. For now, suppose that someone's handed you this probability. And we're going to define a random matrix S that has one non-zero entry. The way we're going to decide what that matrix is by populating the ij entry with the value that comes from the original matrix divided by the corresponding probability. And it will take this value, I have a 1 in the ij entry with probability Pij, and it'll be 0 everywhere else. So first I pick a location, ij, according to this probability distribution, and then I put this number in that entry. So this is a matrix with one non-zero entry. Now what's cool about this is that it's an unbiased estimator for the matrix A. Why is that? Well, we just write down a formula for the expectation. It's the sum of the values of the random variables times the probability that it takes those values. Pij cancel. I get the sum of Aij, Eij. That's just a fancy way of writing A. The Eij are just the matrix units. Okay, great. So we have an unbiased estimator for the matrix. We're done, right? No. Why not? Because a one-sparse matrix is a terrible approximation for a given matrix. And so we need to work hard. So how do we improve the results? When you have an unbiased estimator and you want to improve it, what do? You average copies together to reduce the variance. So let's do that. Let's form a matrix A hat R, which is an average of R independent copies of this random matrix S. How many non-zero entries does this matrix have? At most R, this one. At most R, pointing the wrong place. At most R non-zero entries, it is still an unbiased estimator, and we hope that we've driven out the variance so that it's actually a good approximation. Okay, good. Now how do we pick these probabilities? Well, we're going to analyze how well A hat R approximates A, and then we're going to reverse engineer the probabilities to make the bound small. So I'm not going to go through the details of this, but here's an upper bound for each one of the components of the approximation. It depends on the size of the entries in the matrix and the probabilities. We can compute variances. It's not very hard. We get these things that depend on the entries of the individual matrix, the matrix we started out with, and the probabilities. These are components of the variance. These are upper bounds. And so the matrix Bernstein inequality tells me that the expected approximation error is going to be small when the upper bound is small and when the variance is small. So I want to push both of these down. How do I do that? I make Pij proportional to both Aij, Pij proportional to Aij, and proportional to Aij squared. Okay, then I make the probability, and then everything works out. So the Bernstein inequality is going to tell us what we need to compute to make sure this is a good approximation, and then we're going to compute probabilities to make the approximation good. All right, this leads to the following result. So before I start, remember that we only expect to be able to approximate matrices that don't have a lot of information in them. And information somehow could be reflected in the rank of the matrix, a number of linearly independent columns. As it happens, you need a little bit more subtle way to measure information content. So we're going to introduce something called the stable rank, which is defined as the squared Frobenius norm of the matrix divided by the squared operator norm. This is always a lower bound for the algebraic rank, but it's a continuous quantity. How do you understand this? Well, there are two extremes. If the columns of A are all the same, this number equals 1. Okay? If the columns of A are all the same, this number equals 1. It tells us that there's not much going on in this matrix. On the other hand, if the columns of A are orthogonal to each other, then this number equals the dimension of the matrix. And of course, you can't really approximate an orthogonal matrix. It's got a lot of information in it. So the stable rank is going to be a reflection of the information content. And the theorem, which is due to Kundu and Drenais in this form, is that if you choose the sparsity of your approximation proportional to the stable rank of the matrix times dimension log dimension, so in other words, you need about d log d entries per column, per independent column of the matrix, then you get a good approximation relative to the norm of the matrix. So to repeat, for each sort of independent column of the matrix, you need about d log d non-zero entries in your approximation. And if you want a really good approximation, you need to pay epsilon minus 2. This is the usual sort of central limit theorem behavior. In the proof of this result, the expected error in approximating A by A hat is really an immediate consequence of the analysis I showed you on the previous slide and the matrix Bernstein inequality. So again, this result is both the analysis and the design of the method both depend intrinsically on how big this quantity is, which is explained to you by this matrix Bernstein inequality. Okay. Deep breath. Any questions about this before I tell you about something more interesting? That was a way of moving. Oh, so I did get a question.
Sorry, so I'm just curious, in the original sampling procedure you defined,
Yeah.
because, so is it sure that the matrix you get is a subsample of the matrix, or is it like an approximation?
What happens is you will be, each of these samples is actually not a subsample of the original matrix. You take the entry and you rescale it by the probability. So it actually doesn't look like a subset of the entries of the original matrix. What you have to do is make entries bigger and proportional to the likelihood that you select them. So if somehow you happen to select an entry that were uncommon, you would have to scale it up a lot to
Right. So
deal
is
with
it?
that.
So is this method also like, I don't know the literature, but is it also like graph sampling?
Let me tell you about something else.
Okay.
Hold that thought. More questions? Okay, good. All right, so here's an application which I think is amazing. So this is maybe the best paper I've read in the last 5 years. Fast graph Laplacian solvers. So suppose that G is a weighted undirected graph with n vertices and m edges. All right? So the combinatorial Laplacian describes, this is a generator for a random walk on that graph. Okay? And you might like to be able to solve linear systems in this Laplacian. You can solve a lot of problems in graph theory by framing them as linear systems in the Laplacian matrix and then solving them. Now, the claim at the highest level here is that to solve a linear system in a graph Laplacian, you don't need cubic time in n, the side length of the matrix, which is what you would expect if you were to use a direct method like Gaussian elimination. Instead, you can actually solve this linear system in time that's proportional to m, the number of edges in the graph, which is the sparsity of the Laplacian, the number of non-zeros in L, times logarithmic factors in n and epsilon. So you can get an epsilon accurate solution in time that's linear almost in the sparsity of this matrix. So this is shocking. This is a big class of matrices. And what this is saying is that we have a near linear time algorithm for solving linear systems in this kind of matrix. Linear in what? Linear in the number of degrees of freedom in the matrix L. Okay. So how does this algorithm work? It's based on something called Sparse Cholesky, which is a bit like Cholesky, but it doesn't produce an exact factorization of the Laplacian. So instead of writing L as CC transpose, where C is lower triangular, it approximates L by CC transpose, where C is lower triangular. What kind of approximation? It's approximation with respect to the Wigner order. So in other words, all of the eigenvectors and eigenvalues of this matrix line up with the corresponding eigenvalues and eigenvectors of L in such a way that it's just leave this alone. If you don't know what this is, I don't have time to explain this. All right, so we get a factor C, which is very sparse, and which is a good approximation to the Laplacian L, and we can do that in time that's linear in M. And once we have this factor C, we can use preconditioned conjugate gradient with this factor C to solve the linear system efficiently. So the real goal here is to produce a preconditioner using the Sparse Cholesky algorithm. Okay, what's Sparse Cholesky? Okay, so remember that the Cholesky algorithm takes a matrix and reduces it by picking off the first row, forming the rank 1 matrix obtained by the first, dividing by the first entry in the corner, and the rank 1 matrix you use star, subtracting it off from the bottom block, and repeating. So this is the Cholesky algorithm. You basically form the Schur complement of L2 in this matrix, subtract off this rank 1 matrix, repeat. Why is the Cholesky algorithm expensive? Because it takes n squared time to form this matrix and subtract it off. And that happens in every step. And so the total cost of forming Cholesky factorization is n cubed. So if you really want a Cholesky factorization, it's expensive. So what King and Sachdeva showed is that you don't actually have to do all that work. So here's a character. You say, well, look, you use star as a very simple matrix. It just doesn't have much information in it. It's only rank 1. Why do I need to subtract this entire matrix to form the Schur complement? Can't I approximate it? And so instead of subtracting off this rank 1 matrix, they just throw away most of the entries and subtract off the sparse approximation of this matrix. I already proved to you that sparsification is possible, so you should believe that something like this is reasonable. And so instead of subtracting off any squared things, you subtract off something that's like amortized m over n things in each step. And then you repeat. And what's interesting about this is that the total cost of performing this operation, because you have to keep throwing things away, is really just order m, the total number of edges in the total number of non-zero entries in the matrix. Now, I've lied to you a little bit because this is not actually how the algorithm works. The sampling probabilities are computed in a different way using graph theory. But what I love about this argument is it's based on Bernstein's inequality and a generalization that holds for matrix Markov. And by combining these tools with these ideas from graph theory, King and Sarkeva were able to obtain a maximally efficient algorithm for solving graph Laplacians, which has a lot of implications. And what's even more amazing is this algorithm basically looks like a partial Cholesky decomposition. I mean, it's an algorithm that we know and love and that we know works. And so it feels like this theoretical result is really on the cusp of producing real practical algorithms for solving these problems. Okay, to conclude, I don't think that this King and Sarkeva result would have been possible if we didn't have these matrix concentration results available in the literature. And so we see the cycle of life in applied mathematics here, where these matrix concentration results were developed to deal with specific problems in statistics and data analysis, understanding sample covariance matrices, and so forth. We saw these models, we saw the need for theory, developed theory. That theory has applications, and these applications lead to new models that we now need to understand better. And with that, I'll conclude. I got a little obsessed with this problem and wrote some papers. I have a monograph that gives a sort of overview of all this if you'd like to see more applications. Thank you so much for your attention.
We have some time for questions. I think about not very much
I
time because
apologize
there's a
that
plane
I
to
have
get
to go to the airport about 15 minutes, but I'd be happy to answer questions.
So you assume that the matrix distributions you were looking at were centered at 0.
Yeah.
Is that simply, how difficult is it to relax that assumption?
It's straightforward.
Is it straightforward?
Basically what's happening here is you're looking at fluctuations of this around its mean, and I've just suppressed the mean by setting it to 0. The results look a lot more complicated if you don't do that. But putting back the centering is formally straightforward.
Is there maybe anything you could relax in the sense that instead of bounding the, I think that's the spectral norm of the component matrices, you have some nice strict bound on the probability that the spectral norm is above a value? Is that maybe a possible relaxation extension as well, in kind of the same vein as John's question?
I'm not sure that I follow.
Well, as in these samples have like a strict bound on their spectrum.
Oh yeah, absolutely.
Instead
It turns out that if you just want the expectation bound, the right thing to put here is the expected maximum square of one of the summands to the 1/2 power. Okay? So it's much weaker, but you don't get the necessarily the exponential tails if you do that, which sometimes we care about. Yeah, more questions? Yeah.
Are there any, I guess, not obvious challenges to extending some of the results that you find in random matrix theory to the case where you have infinite dimensional operators?
No, this stuff all works well. So it might be that this result, as stated, does not extend to infinite dimensions, but there are versions of these results that apply in on the class of bounded operators on Hilbert space. I'm not sure whether these methods extend, but there are methods that do extend to that side. And so things like this are for sure true. But one thing I will say is that the operator norm is intrinsic in this approach and these results, and you can't get other norms this way. If you want other norms, you have to do different kinds of things.
Is there a simple explanation for the dependency on the dimension?
Yeah, there is. Here is a random matrix that you don't like. So with probability 1 over n, put a plus minus 1 entry in the put a plus minus 1 entry in a randomly chosen entry of the diagonal. Or actually put a Gaussian there. Maybe that's better. So with probability 1 over n, pick each entry of the diagonal, and then in that chosen entry, populate it with a Gaussian. And then add n of those up, and you'll get a diagonal matrix of Gaussians. Its spectral norm is the maximum among those n Gaussians, which is roughly root 2 log n. So the dimension appears in those examples. There's also a coupon collector issue that can come up for other models where it takes n log n draws to collect n coupons, and this is another reason that the logarithm is essential. Unfortunately, there are a lot of examples where the logarithms don't belong, but we really have no idea how to, we really have no idea the general formulation that allows you to remove them. So, research.
Can you do this with higher order tensors?
No. Unless you treat them as matrices, then that's different. I mean, you can certainly do this with Kronecker products, but those are just fancy matrices.
Can we relax? Can we relax the boundedness of SK to some sort of like light tail matrices?
To what?
To light tail matrices in some sense?
Yeah, absolutely. This is what I sort of indicated before. At least if you're really interested in this expectation bound here, the quantity that you should replace, that you should call L, is the expected maximum square of one of the summands to the 1/2 power. Okay? So if all you care about is the mean, then you can put that here instead of L. And so that actually works all the way down to matrices that have 2 moments. Yeah.
Great. Well, thank you. Very great.